Alright, so we're finishing up 8.3, looking at the infinite geometric sequence. You can see here we have the terms of a geometric a sub 1 times r, a sub 1 times r squared, times r cubed, and so on. We're multiplying by r every term, and it goes on infinitely. There are certain cases where we can find the sum of that entire infinite sequence. Okay. The key here is that our sequence has to converge. Okay, it has to converge to 0. And the way it does that is the relationship you see here in this initial part. The absolute value of the common ratio has to be less than 1. Okay? Now, we mentioned already that a geometric has kind of an exponential relationship. Okay? Exponentials, however, can go like this. Alright? Or if this r is a fraction, how would that look? How would that look?
It's kind of like going to that.
Yeah, it's going to go like this instead. Okay? It's going to go like that. It's not going to go, you know, up fast and level off. That's more logarithmic. Okay? But what we have here, when your common ratio is less than 1, is something that looks like that. Okay, now understand, we're still dealing with a series, so it's actually only defined on the integers. Okay, let me get a different color here. So it would be defined right here, and at 1, and at 2, and at 3. Okay, and actually it wouldn't technically be defined there because it's only positive integers, so let me fix that. Okay, but you'll notice what's happening to the value of each term. It's approaching 0. Okay, that's the key. It is also possible if we have a negative r, as long as it's still the absolute value is smaller than 1. Let me show you what would happen in that case.
What if it is 1? Can't be 1.
If it is 1, then you don't have a geometric. You have a constant. If r is 1, then you have a constant function. It's just a flat line. Okay. If you have a negative r, however, remember what happens to the terms because r is negative. Yeah, the signs alternate. Good. From positive to negative. So, when you have a positive 1, come on. When you have positive 1, I want this dropped. Oh, because it's still in red. Switch. There we go. Okay. When you have a positive 1, the r is going to be to a negative, is going to stay negative, so it's going to be down there. But then when you go to a positive 2, the negative is going to be squared, so you're going to be up here in a positive. At 3, the negative is going to be cubed, so it's going to stay negative, and you're going to be down here. And it's going to keep jumping back and forth, but it will still continue to converge to 0. It will just be going back and forth, almost like a bouncing ball. Okay, and it starts going smaller and smaller. But it goes back and forth. All right. Now, the formula here has this sum, okay, and the formula is actually really, really easy. A sub 1 over 1 minus r. Okay? The sum from I equals 0 to infinity of a sub 1 times r sub I is a sub 1 over 1 minus r. Okay? So a sub 1 over 1 minus r. What in this case would a sub 1 equal?
4.
Okay, 4. 1 minus 1 is 0, so 0.6 to the 0 is 1, times 4 is 4. What is r?
0.6.
0.6. So we have 4 over 1 minus 0.6. Okay, that's all there is to it.
Do you leave it like that or just?
No, you would find the value. Okay. That will end up being 4 over 0.4, which is 10. Good. Sometimes if you have a 5A and 5B, so you don't have a lunch, they'll let you, but not just whenever. Thank you. Alright, so does everyone understand how we can use that? Alright. We did this one before in kind of a different context, but here we can do it actually even easier. Okay? The sum of this entire series, starting at 3, 0.3, 0.03, 0.003, alright? What would a sub 1 equal?
3.
3. And what would r equal?
0.1.
0.1, okay? We're dividing it by 10 every time, or multiplying by 1/10. So, 0.1. So the entire sum would equal 3 over 1 minus 0.1. Okay? That's 3 over 0.9, which ends up equaling
10 thirds.
yeah, 10 thirds or 3 1/3. Okay? So we saw this one logically. We saw that, hey, it's just going to keep adding a decimal point of 3 each time, but now we can see that we can kind of confirm from our formula that it works that way as well. Alright, any questions about the infinite geometric series? Comments or anything? Yes?
What if n is equal to 0?
Remember, what we can do is you can always find a term manually if you need to. So like if it were n equals 0 to infinity, you could just figure out what 0 would be. What would it equal when n equaled 0, and just add that to this. Anything else? Okay. One application I wanted to look at that was kind of interesting. It's an application actually of the partial sum, and that is what's called an increasing annuity. All right, this is a way of saving money where you're putting away a certain amount each month. Okay. Now this, when you get a job at some point, you'll probably have this as an option, okay? If you work in a company, they might offer a 401k. All right, now the only difference between that and what we see here is, so we're going to assume, to keep things simple, that the percentage rate stays the same, Okay, you could do this with a real 401k if you looked at like your average percentage. But how much are you going to have at the end of your investment if you continue to put, in this case, $50 away every month and you make 6% interest compounded monthly? Okay? In this case, we're going to save for 2 years. But let's look at how this would work. First of all, come on, there we go. First of all, what we're going to do is use the compound interest formula. Now, we haven't covered this year. How many of you have seen that in previous years? Okay, compound interest. There's some kind of variation of that. Okay. I'm going to enlarge this because that's kind of hard to read. Okay. So here we have the amount at any given time, that's what A stands for, equals P, the principal, which is the starting amount, times 1 plus R over N to the NT. R is your interest rate, which is a percentage, so you would write it as a decimal. And then N is the number of times that you are going to compound the interest every year.
So once.
Well, it depends on the problem. In this case, we're compounding monthly, so N would equal 12. All right? We're compounding monthly, so N equals 12. All right? This 6%, R is 0.06. Okay? P is going to be 50. Now, here's the deal. Because our total principal is changing every month, we're going to have to consider this on a month-by-month basis. Okay? Each month, you are depositing $50. So we're going to consider that $50 as the principal for each month. All right, now let's look at how we would deal with this for the first month. Okay? So the amount for month number 1 is going to be principal, which we said was 50, times 1 plus R over N. We already said R is 0.06 and N is 12. Okay? Now, this first month, how long is it going to be invested for?
0 months.
No? The full 2 years. Okay? The full 2 years.
So 24 months.
So, yeah.
T is 24.
T equals 2 years. Alright? Now, the 24 comes in because look at our formula. It's N times T. 12 months times 2 years gives us 24. Alright? And you'll notice here, that's how many times it's going to compound. Okay? So this original $50 is going to grow 24 times. Okay? How much does that ends up equaling 56.35? Okay, so let's round it to 56.36 to round to the penny. Okay? Now, we could do that for all 24 months and add it up. Okay? What's your question? Or?
No.
Okay. If I were doing month number 2, let's change colors here. Month number 2. Month number 2, again I have $50. It's the 1 plus 0.06 over 12. But in this case, remember we said this is how many months it ended up equaling. So rather than figure it all out again, how many months will month 2 grow? 23. Okay? It wasn't there the first month, so now it only has 23 months to grow. Okay? Sorry.
Do you multiply the 23 by 12?
No. Actually, technically, the time here would be 1 and 11/12 years.
Yeah, but the formula is n times t.
Yes. And t is always in years. Because basically what this is doing is it's converting your time from years to months.
Okay.
Or if it were compounding quarterly, it would be converting from years to quarters or whatever. Okay. We'll look at the formula itself a little more closely when we get to exponentials, our unit on exponentials. But yeah, so technically our time here is always in years. It's 1 and 11/12 years. Or 23 months. Okay? Now, this continues on with this same pattern. And until we get down all the way to month 24. Okay? Month 24. The amount that we're going to have there is 50 times 1 plus 0.06 over 12 to the which power? 1. That last month, it's only going to grow for 1 month. Okay, because we were saving for 2 years, so we're down to the last month. There's our last deposit, and it's going to go in for 1 month. Now, rather than figure out all 24 amounts and add them up, we can view this as a geometric series. Okay? Let's consider it. And what I'm going to do in order to do this is I'm actually going to look at the months kind of in reverse order. Okay, so this is going to be the first term of my series because it's growing for 1 month. The 23rd month is growing for 2 months, so it's going to be the second term, and so on. So if I were writing this as a series, I could say that I have the sum from I equals 1 to 24 of 50 times 1 plus 0.06 over 12 to the I power. Okay? Or we could use n's, it doesn't matter. But does that make sense? The advantage to writing it this way and recognizing it as a geometric sequence is now we can use our formula. Okay? Yeah, did you have a question?
Yeah, what's the... I'm just trying to find the difference between that and what we were doing before. Like the same way that you were putting the months out.
Well, the difference, you mean this?
Yeah.
That's the thing. It has the same format, okay? And we're writing the sum, and what we could actually find this sum by doing 1, 2, 3, all the way up to 24. The nice thing is, though, if we recognize this as a geometric, remember we have our formula. A sub 1 times 1 minus r to the n over 1 minus r. Right? So, the only term I actually have to figure out is this amount right here. A sub 1. Okay?
It's 50.25.
That's 50.25. Good. So now we have 50.25 times, and here's where it can get a little bit messy, because watch this. we have 1 minus, what's R?
0.06.
No.
It's 1
1
plus
plus
And
0.06.
wait, since we said that, okay, here's where you have to be careful. Notation can mean different things in a different context. The R right here is not the same as the interest rate, right? Because we're dealing with a different formula. This R stands for the common ratio in our geometric sequence, right? What's the common ratio in this geometric sequence?
1 plus 0.06 over 12.
1 plus 0.06 over 12, this whole thing. Okay? If you were to simplify this, you would get 1.005. Okay? So do be careful about that. I'm glad you guys actually said that because it's really easy to make that mistake because this R is not the same as the original R. Different formulas. So we have 1 minus 1.005 to the n. N is 24. That's over 1 minus 1.005. Okay? Now it's just a matter of using our calculators carefully to come up with our solution. Okay? Let me show you one thing, however, with the calculator. Alright? Will this actually still work or no? No. Yes?
How did I find A sub 1?
A sub 1? A sub 1, all I did was, it was this last term, okay? Remember back here, wrong slider. Back here, this deposit was growing for 24 months, this deposit was growing for 23 months, 22, 21, and I said the one thing that we would do is we're going to consider the deposits in reverse order, okay? So A sub 1 would actually be that deposit we made in the last month that only got to grow for 1 month.
So to find A sub 1, we have to just put it to the first power.
Yes. Yes.
So it's 1,277.96.
That sounds
That's
right.
what I got.
Okay. Let me show you something with the calculator though that'll make this, that can make this a little easy. Okay? Here's the deal. I just told you that 1.005 was what this equaled. Okay? One thing you can do to make your life a little bit easier is use the store feature on your calculator. Okay? Because you're probably going to use your calculator to figure out what this equals anyways, right? So if I do 1 plus 0.06 divided by 12, and I figure out that that's 1.005, since I have it there, you see this stow button? Okay? That's going to store something in a variable. Alright? So this is kind of cool. You can use whatever letter you want, but if I hit that stow button, see the little arrow that pops up? That means I'm going to put this answer in some variable. And I'll just hit, you can hit whatever letter you want, but I'll just hit this to give me an X. Okay? Once I hit enter, every time I type in an X, the calculator is going to see 1.005. Okay? This is really, really helpful, especially if you have a long decimal and you don't want to round till you get to the very end of your solution. Okay? So I have 1.005. Now when I plug this in, I can actually type in 1 minus x to the 24th power. Okay?
I should put parentheses around the X.
No.
You know?
No.
Does it for you?
This follows the order of operations. Order of operations says do the exponent before you do subtraction. So it'll do it right this way. So we've got that. That's going to be your numerator. Then we need to divide that by, and this I will put in parentheses because I want to divide by the whole denominator. But I can just type in 1 minus x. Whoop. 1 minus x. Close my parentheses. And that is the entire, what's in the parentheses. So I have 50.25 times that. Okay? Does that make sense? Yes?
How do you clear it from the x? Like if you want to just use x.
Well, that's the thing. Your calculators don't have like algebra capabilities to recognize x as a variable to solve for. So you're not going to do that. And plugging something in x here, if you go to use your y equals and graph it, it's not going to see it as that value in that context. So, because there, what the computer's actually doing is plugging in a bunch of different values. That's how it gets all the points. So, all right. So 25.43 is what we got here. Okay. You don't need to worry about it.
Because I just hit X and enter and it says 1.015.
Yeah, it'll stay in there,
Okay.
but that's not going to affect anything else unless you wanted to use X for a different value. And in that case, you just store something else over it. It'll just overwrite whatever was in there.
So, like, if I wanted to do like 5x plus 3, it would get rid of the whole like 1.05.
No, if you type in 5x plus 3, it'll do 5 times 1.005 and then add 3.
So then what do I do if I need to plug in something? And, for like graphing, like if I did the graphing,
Well,
can I do
when you
5x?
go to graphing, that's what I was telling him. When you go to graphing, it's not looking at the 1.005. It's automatically plugging in a bunch of different stuff
Okay.
for that. Okay. All right. So just to finish off, 50.25 times 25.43, and you guys got what? What was it? 1,200.
1,277.96.
Okay. And that is money, so we'll wait what is such. Okay. All right. Listen, what I'd like you to do. Listen up, please. If you're talking, you're not listening. What I'd like you to do is page 607. Okay? That same study tip I showed you in the problem that we just did is actually on page 606. So you can see that. So these are the problems. You will need to go to the textbook to get this because there isn't a separate smartboard file for these problems. Try these. We will take questions first thing on Wednesday. Then we'll do your quiz. Then we'll move on. Okay? So come with questions. There's not going to be a do now on Wednesday because we're going to just jump right in and do your quiz. Yes. Yes, this is a summative right here. Okay, so this will count for a grade. This will be your first grade of the year.
It's like 10 points.
Okay. No, it is. No, that's them. How many is it? 34. 34 points. Okay. So,
34 questions?
34 points.
Okay.
So, all right. So, there you have it. Have a great day, guys. All right, you too.